Hello, and today for College Algebra, we're doing P4, which is all about factoring polynomials, sort of breaking them apart and like dividing, kind of. So, if I'm factoring, I want to factor out a common monomial, aka I want to look at everything and what can I easily divide all those terms by? Well, they all have at least an x, and all those numbers are divisible by 2, so I'm going to factor out 2x. Well, if I divide 4x cubed by 2x, that would just give me 2x squared. If I divide negative 6x squared by 2x, that's going to give me negative 3x. And if I divide 12x by 2x, that's going to give me 6. Now this number is much easier to, or this polynomial, excuse me, is much easier to factor in the grand scheme. When I factor trinomials, the first terms attached to my x want to be factors of a, aka they want to multiply whatever number that is. And these numbers, whatever I'm here, want to be factors of c, whatever is right here. So if I'm using that previous example of 2x squared minus 3x plus 6, right? Plus 6. I would want these two numbers in blue to multiply to 2, so something like 2 times 1 or 1 times 2. And these numbers here in green have to multiply to this 6. So it could be any combination of 1 times 6, 6 times 1, 2 times 3, and 3 times 2. Of course, we have to figure that stuff out and get creative, and we can use typically the b term to determine that. So let's try a couple. Here we have 2x squared plus x minus 15. Now, one common trick that I'm used to is I can multiply my first term and my last term together. So I can get 2 times negative 15, and that's going to give me negative 30. Now, what I want to do is I want to find two numbers that multiply to negative 30 that add to whatever my b term is. In this case, my b term would be 1. So I want to find two things that multiply to a times c and that add to my b term. Well, what multiplies to negative 30 adds to 1? That would, of course, be 6 and negative 5. What I'm going to do is my first and last term, 2x squared, and negative 15 are going to stay. And I'm going to replace plus x with plus 6x and minus 5x. Now, if I were to combine 6x and negative 5x, I would get plus 1x. So conceptually, those are equivalent statements. Now, why would I do this? Well, there's a neat trick that whenever I have an even number of terms, in this case I have 1, 2, 3, 4 things, it's called factor by grouping, is I can factor out something of just this group. So what can I divide 2x squared plus 6x by? Well, that would be 2x, leaving me with x plus 3. And now I have to look at these ones. And I want to divide those two terms by something that would give me exactly x plus 3. In that case, I would divide it by negative 5, and I would get x plus 3 there. My factored would be the matching pair, x plus 3, and the outside pair, 2x minus 5. Otherwise, I could, as we talked about earlier, use this pattern here to sort of guess and check situations that would work. In this case, numbers that that multiply to 2x. So I would know that one has to be 1x and the other one has to be 2x because, well, there's only 1 times 2 that multiply to give me that. So 1 times 2. And here, this negative 15, I would have, of course, 1 times 15, 3 times 5, 5 times 3, and 15 times 1. The other thing I would notice, of course, it's a negative. So one of these numbers in these multiplication pairs has to be negative. And I would also notice that this middle term is only 1. So I want it to be pretty small, which means, like, logically speaking, when I distribute it out, the 15 is just too big. So I have it narrowed down to 3 and 5 in some way. Well, if I put the 3 here and the 5 here, and let's say we make this negative and this positive. Well, 5 times 2x would be 10x, and x times negative 3 would be negative 3x. That would give me 7x for a middle term, which is not what I want. I want just 1x. So instead, we could try, putting the 3 here and the 5 here. And let's say we put the minus here and the plus here. Well, negative 3 times 2x would give me negative 6x, and x times 5 would give me positive 5x. That'd give me negative x, so I would know I would just flip the signs. So if you don't feel comfortable with this process, you can sort of guess and check through that way. It's just that I find the structure of this process tends to be more efficient. Here we got another one. So again, I'm going to follow this pattern, but if you want to do this sort of layout of guessing and checking these things, feel free. So I'm going to get 2 times 3 is going to give me 6. So I want two numbers that multiply to 6 that add to my current b term, which would be negative 5. Well, if it multiplies to a positive number, it's going to add to a negative number. It's probably going to be two negatives. So the first thing that comes to mind is negative 2 and negative 3. The nice thing about this process of breaking up my middle term is it technically doesn't matter the order you put them in. I'm going to put negative 2x minus 3x in there first, but I'll show you the order doesn't matter. So what can I divide both those by? That'd be 2x, giving me x minus 1. And this one would be negative 3, giving me x minus 1, giving me x minus 1 and 2x minus 3. Well, if I were to flip the order, we have 2x squared minus 3x minus 2x plus 3. The only thing I can take out of this first group is x, leaving me with 2x minus 3. And here I'd have to take out a negative 1, leaving me 2x minus 3. My matching pair would be 2x minus 3, and my outside pair would be x minus 1. Again, remember from yesterday, these multiplication things are commutative. Order doesn't matter. So these are equivalent expressions. So if you're going to do the break up the middle term method, it doesn't matter which number comes first. All right, factor completely, make sure we can break down everything. So the first thing we should always check, what can I take out of everything? In this case, I could take a 4 out. Give me x squared plus 4x plus 3. Now, one thing to note, if I go back, this methodology of a times c always works. I typically do it when my a term is not 1. If my a term is 1, in this case, the a term that matters is this 1 out here, I know I'm just going to have x and x. So I really only have to worry about this process right here, what multiplies to 3, in that case, 3 and 1. That multiplies to 3, that adds to 4, of course. And then the 4 stays out. Okay. Some special factors, we talked about them yesterday, only in the reverse, where you can just use the formula to find the patterns. Here, same idea. If I recognize a pattern, I can factor and break it down immediately. So here, we have 3 minus 12x squared. First thing is, I can divide both by 3, giving me 1 minus 4x squared. Anytime I have two things, or two terms, excuse me, in this case 1 and negative 4x squared, especially if I see a minus in between. Anytime I see this, I'm looking out for if they're perfect squares or not. And in this case, I would look at each number. Does 1 have a perfect square root? Of course, it's 1. So the square root of 1 is 1. And does 4x squared have a perfect square root? Of course, that'd be 2x. So I know that this is a difference of squares problem that follows the pattern a plus b, a minus b, where a in this case would be 1, and b in this case would be this 2x. So I'm going to leave the 3 out front. We get 1 plus 2x and 1 minus 2x. Okay. Over here, there's nothing I can take out of both of them, but again, I have two things and a subtraction sign. So the first thing I would want to check is, are both of those perfect square roots? Well, if I are perfect squares. Well, if I square root 16x to the fourth, square root of 16 is just 4. Square root of x to the fourth would be x squared. And if I square root 81, that would be 9. So these are perfect squares. So I would get 4x squared minus 9 and 4x squared plus 9. Okay. Down here, well, I can look to factor this if I certainly wanted to. I could also recognize that both of these terms are perfect squares. This would, of course, be 4x, and this would be 3. So I could look to check if it's just the sum of perfect squares. So let's take a quick look. 4x times 3 would be 12x. 3 times 4x would be 12x. So would that give me the exact middle term? I would say yes. So this one, of course, is 4x plus 3 quantity squared. Otherwise, of course, we could factor it out by hand. So I could do all sorts of interesting things like 16 times 9, which would give me 144. And now I would need to find what multiplies to 144 that adds to 24. And that would, of course, be 12 and 12. So we would get 16x squared plus 12x plus 12x plus 9. What can I take out of these two? That would be 4x, giving me 4x plus 3. What can I take out of these two? That'd be 3, so 4x plus 3. Inside matching pair, 4x plus 3. Matching or outside pair, 4x plus 3. So either way, as long as I have a good math foundation, I get the same result. Sometimes if you can just recognize patterns, it's a little easier. For example, if you didn't recognize patterns on this second one, for example, 16x to the fourth minus 81, you could have 16x to the fourth plus 0x minus 81 and factored it traditionally. You would just notice that instead of x to the fourth, this should be x squared. This would be x to the fourth, so I'd have to have x squareds here, and then I have to find numbers that multiply to 16 and that multiply to this 81. Because typically speaking, if you're going to factor, your terms, your degrees, follow a pattern of 2 to 1 to 0. You guys are traditionally used to the 2, 1, 0. Well, it works too if it's 4, 2, 0, as long as they have that 2 to 1 relationship. Okay. X to the third plus 8. I'm looking at this one and I see that it's a perfect cube. And then my question becomes, is 8 a perfect cube? Well, if I cube root 8, I get 2. So I know that this is perfect cubes. So I can go back to the formula and factor that out. I know that a plus b cubed results in this equation right here. So that's going to give me, let's see, a plus b, a squared minus ab plus b squared, where my a term is going to be x, because that's what's being cubed. And my b term is going to be 2, because 2 cubed gives me 8. Everywhere there's an a, I can plug in an x. Everywhere there's a b, I'm going to plug in a 2. So I get x plus 2. X squared minus 2x plus 4. And that's actually as further as I can go. Here, I can divide both by 2. X cubed minus 27. And again, same idea. I can note that x cubed is a perfect cube, and is 27 a perfect cube? Well, of course it is. It's 3. Well, that's terrible, 3. So I can follow the exact same thing of a cubed minus b cubed, which would be a minus b, parentheses, a squared plus ab plus b squared. So I would get the 2 out front, which I didn't adjust from earlier. That gets dragged down. And then I would get x minus 3, x squared plus 3x plus 9. Ooh, 8x squared plus 51x plus 18. Well, again, 8 times 18 gives us 144. So I'm looking for two numbers that multiply to 144 that add to 51. And let's see, let's try, 48 and 3? So we would get 8x squared plus 48x plus 3x plus 18. Factor out 8x, give me x plus 6. Factor out a 3, so x plus 6. Shoot. So we would get x plus 6 and 8x plus 3. Here I only have two things, so when in doubt, take out whatever they both have. So they both have an x squared. Leave me with x minus 1. If you start with 4 things, you can factor by grouping immediately, kind of what we've been doing the entire time. So here, what can I take out of x cubed minus 2x squared? That, of course, be x squared, leave me with x minus 2. And then what I have to take out of here to give me exactly x minus 2, well, I can, of course, take out a negative 3. So my answer would be x minus 2, and of course, x squared minus 3. And graphing can be used to factor trinomials. That's kind of what I've been showing you the entire time. However, you can also see page 38 in reference on your textbook if you want to see how it's done that way. Okay. Otherwise, that's all I got for you. Thank you for listening, and I hope you have a great day.